Greetings and welcome to Distilled. In the previous lecture, we had talked about functions and we mentioned that over time in subsequent videos, we'll be using functions very often. So you'll get familiar and comfortable with this concept as well. In today's lecture, we are going to introduce another very interesting and important tool that is available in Python, and that's called fsolve. Okay, so fsolve actually comes from this library spicy.optimize. So just like NumPy is the library that is very often used for linear algebra and all the mathematical calculations in Python. SciPy is another library that is very useful for performing very complex scientific and mathematical calculations, right? So this is also a very useful library, and one of the key functions from this library is fsolve. So we'll be talking about that. And fsolve is basically used for evaluating, for solving non-linear algebraic equations, right? So, so let's define what are non-linear algebraic equations. And then we'll see how we could use fsolve to solve these nonlinear algebraic equations. All right. So any equation, it could be an equation of a single variable, it could be an equation of multiple variables, can be eventually written in the form of fx equals to 0. The vector x implies that there are multiple variables on which this particular function or this particular equation depends, right? So this is how you can write any particular equation, right? Now, if you want a unique solution, you definitely want the same number of equations as you have the number of variables. So if you have 10 variables, you would need 10 such equations, right? So let's say you have n variables. So we would use n equations to solve this problem. So this would be f1x, f2x, f3x, so on till fnx, right? And if we put all of them together in a vector, we get fx equals to 0, right? So most of the numerical math textbooks or any other tutorials that you'll see, you'll be able to define a system of non-linear algebraic equations in this way, right? This is how you can define any system of non-linear algebraic equations. So one thing that you can see from here is that when you are defining the function that is basically equal to 0, that function is going to be a vector, right? So let's say you define some f, which is a function of the x vector. Let's write a capital X over here for Python, right? What you'll return after all the calculations is going to be an array, right? It's going to be an array, and this array is going to be of the same order as the length of the X array, right? So for a unique solution, right? So you would try to have the same length as the length of the X array, right? So that is what you're going to return. So this is going to be the array that you're returning, right? And in order to find the X that satisfies this system of equations, what we would want is that this array that we have returned should be, all the elements of this array should be 0, right? Or close to 0, right? So all the non-linear algebraic equation solvers that are developed, they are developed such that with respect to all the variables, these values of the returned array should be as close to zero as possible. Right. And people do that by defining various kinds of loss functions. They perform various analytical, numerical, etc. calculations to describe appropriate methods to solve a non-linear algebraic equation. So that is all that we are trying to do. We are trying to minimize all the values in this particular array. One very simple method to sort of minimize all of the values, this is something that we've seen in linear regression as well, is by taking the sum of squared errors, right? Taking the sum of squared errors, since we are the true value is just zero for our case, we'll just say sum of f squared, and we'll try to minimize this with respect to each x, right? So we'll try to put that equals to zero, and this itself gives us the set of equations that we need to solve in order to get the variables, right? But then the problem here is that these equations itself, whatever we are getting, this itself could be non-linear in nature, right? These itself could be non-linear in nature. So you could perform multiple iterations and so on and so forth. But the basic idea over here lies lies that you're trying to uh, go through the values of, or you're trying to select the values of all elements in the x vector over here, such that the values in the returned vector over here are as close to zero as possible, right? And even if a single value in this entire returned vector is greater than the threshold that you've set, so there could be a threshold value that, okay, if all the values of this returned vector are less than 10 to the power minus 4, that means we have solved the problem. But if any value, all of them, let's say, are 10 to the power minus 4, but one that is greater than 10 to the power minus 4, that could be 1, there could be 10, 100, anything, right? If any value is there, that means you've not been able to solve this problem, right? So this is the basic idea behind solving non-linear algebraic equations, right? You're trying to minimize the vector that you return here. And one such algorithm is used by fsolve as well. So in this lecture, we won't really worry about what algorithm it uses. We'll just see the syntax behind it, and we'll try to apply it to a problem in thermodynamics. But we could as well discuss, or there are definitely textbooks in numerical mathematics that would have discussed multiple algorithms that are used to solve these nonlinear algebraic equations. We are not going to specifically worry about these algorithms, and we are directly going to use the inbuilt packages so that we go directly towards applications of these numerical tools for chemical engineering, right? So with that in mind, but the way this function has been defined, this is important, right? So this function is what we have to define as the first step to solve the system of nonlinear algebraic equations, right? So this is the function that you really need to define. So this is the step 1 of your problem, right? And the step 2 is calling fsolve, right? So I'll maybe just erase all of this, and then we'll see how to deal with fsolve. So we have scipy.optimize, a library that is used for complex mathematical calculations, just like NumPy, right? This could be useful for performing the polynomial fitting or curve fitting in general. It could be used for solving nonlinear algebraic equations and multiple other such complex mathematical and scientific calculations can be done using scipy, right? So from this, we are going to get fsolve. So it is just fp.fsolve that is useful for calling the fsolve library, right? Sorry, the fsolve function. And then there are two arguments that you need to pass in this fsolve. There are a bunch of other options that are there, but there are two major arguments that you must pass in this function. The first is the function itself. So the function itself implies the function that we had defined. So the so as we had seen that we can write any nonlinear algebraic equation in this form. So this function that we had defined, that we had returned an array, right? Yeah. So the function for which we had returned this array, this function itself would be passed into the fsolve library. So you do not provide any arguments, nothing. You just write the name of the function that has been defined over there, right? And the second argument is x naught, which is the initial guess. Now, this is a requirement in the fsolve library. This initial guess depends on the problem that you are solving. If the initial guess has some physical relevance, if the initial guess is something close to which, because there could be multiple solutions because it's a non-linear equation. So just like quadratic equation has two roots, cubic equations could have three roots. Similarly, any non-linear algebraic equation could have multiple solutions, right? So the initial guess that you provide is basically to choose which solution, or the solution close to which value is you're trying to choose, right? So we'll see an example. So for example, if you're trying to solve, say, x squared minus 4, right? So now this particular function would have two solutions, plus and minus 2. So let's just do that as an example. So let's define the function. And there is only a single variable x in this. So we don't have to pass an array to this. It's just a value. Okay. And you return x squared minus 4. Right? Because x squared minus 4 equals to 0 is what we are trying to solve. Right? So to solve for this, we say sp.fsolve. We write the name of the function. The name of the function is just f, and we'll provide an initial guess. Now the initial guess could be 1, right? Or it could be, let's say, -1, -3, and so on and so forth. So let's just say we have the initial guess as -1, and let's say xs, x solution, is where we are trying to store this, right? So xs is going to be an array, right? And the value that it has given us is 2, which is closer to the initial guess 1, right? Let's say if you would have taken -1, in that case, the solution would be -2, because this solution is closer to our initial guess. So basically, most often fsolve returns the solution that is closest to your initial guess, because it uses an algorithm that just wanders around slowly the initial value that you've chosen, and therefore you get the result close to your initial guess, right? So this is the idea. You could have a set of variables, say x squared minus 4 is one equation, and let's say xy equals to 3 is another equation, or xy equals to 2 is, let's say, another equation, just saying. So in this case, the argument that you're passing, which is x vector over here, so the arguments that you can pass must actually be arguments in terms of an array only, right? So you cannot say fx comma y. That's going to give you an error. You can say only fx, where x0 is, so I'll show you actually. So you could say f capital X, and then small x is x0, and small y is x1. So basically you've passed the the variable over here, capital X, as an array, and the two variables are x0 and x1, right? Uh, Often people do not define these variables this way, so they just end up using x0 and x1 in the return command. So that's what we are going to do. We are going to just say return x0 squared minus 4. That's the first value. And the second equation that we are going to solve is xy equals to 2, or x5 minus 2 equals to 0. So that's x0 times y0, x1, which is y, minus 2, right? And this you have to return as an array. This must be an array over here. So this is returned as an array, right? Or a list or a numpy array, whatever, right? And then once again, to solve this problem, you provide the initial guess over here as an array, because you have passed the argument into the function as an array, right? So it could be minus 1 comma 1, let's say, right? And this would give you an array of the x and y variables that you've tried to evaluate from this. So the value of x that we found is minus 2, and the value of y is minus 1, which is the correct solution, right? If we would have given, say, 1 comma 1, then we would then in that case we would get 2 comma 1. The x is 2 because it's closer to this 1, and 1 is the value closer to y, right? So there could be a bunch of other this is a very simple set of equations, and because of that we've got a very simple result right now. But there could be more complicated nonlinear equations which may not give you answers as easily in a more straightforward way. So in that case, you could use better algorithms, you could use better functions from Python. But to get started, I think fsolve is a good tool to get hands on the solving of nonlinear algebraic equations, right? So now let's go to an application that is relevant to chemical engineers, and that's from thermodynamics. So in one of my previous lectures regarding thermodynamics, I have taught about these equations of state. So we all know that ideal gas equation of state is a very good model applicable for high temperatures, low pressures, right? But as you start going into the limits of moderate pressures or moderate temperatures, wherein the interactions between different molecules of a gas become important, ideal gas equation starts to become less and less useful, right? Less and less accurate. So therefore, we try to use better equations of state. So there are multiple equations of state. One that is that has been quite well used and well defined is the van der Waals equation of state. And I've talked about all of this in my equations of state video, if you would like to go and check that out. So and this problem as well, we have actually solved this problem using Newton-Raphson method. And over there, we had solved it manually, like we had done those calculations by hand. But now, since you know Python, you could actually solve this using Newton-Raphson. You could write a code for Newton-Raphson method using Python as well. So that would be a very good exercise because now you're familiar with Python, right? So that would be a good exercise, but let's not do that today. Let's try to use fsolve to solve this problem, right? So let's write the van der Waals equation of state, right? So the van der Waals equation of state is written as P plus A by V squared times V minus P equals to RT, right? Where V is the molar volume and A and B are the van der Waals coefficients, right? Or van der Waals constants, right? So that's the equation of state, right? Now in this, we are trying to solve for volume, okay? We are trying to solve for volume over here. So that implies if we want to use fsolve over here and we set it up as a problem for non-linear algebraic equation, we are going to write this in the form of fv equals to 0, right? That means towards the RHS, we must have just 0. So let's bring everything to the LHS. And therefore, the function f is just p plus a over v squared times v minus p minus rt. And we'll try to minimize this function, right? We'll try to minimize this function and bring it closest to 0, as close to 0 as possible, right? So this is the problem that we have to solve, okay? So we could directly just define a function that has this value, okay? Like that is calculated by doing this. It should have v as an argument, right? And we should be able to use that to evaluate the volume, right? So let's do that. So let's first define, I'll just comment this part out, and let's define the function for van der Waals, right? Its argument should be v, right? And what it should return is p plus a by v squared, v squared times v minus p minus rt, right? That's what it needs to return. But over here, we don't really have a value for pressure A and B and R and T, right? So here I would want to define something called as local variables and global variables. Okay, local versus global variables. So now, when you start learning about functions, this is something that would separate different variables from each other. So there could be local variables. These variables are defined within the function, right? These variables are defined within the function, okay? Global variables are variables that are defined outside the function, or basically they are defined in the main code, right? These are defined in the main code. The main code is the code where you call the function, right? It is not necessary that you just call a function in the main code, but basically you get the idea, right? The main calculations you perform are in the main code, right? So any variable that you define inside a function is valid only as long as the function, you're performing any calculations with that variable inside the variable, the function, right? So let me just take a slight detour. I'll comment this out and come back to it. So for example, if I say def f of x, I define a variable a equals to 2 and let's say return a plus x, right? That makes sense. But so over here, a is a local variable because I have defined the value of a inside my function f, right? But let's say I try to print this a outside my function. I would actually see an error because there is nothing defined as a outside in the main code. So as long as you're performing some calculations with this variable inside the function, that's fine. But you cannot use this variable outside my outside the function, right? So this variable is known as a local variable. So the local variable is something that you can use only inside the function. It cannot be used outside the function, right? The second type of a variable is a global variable. A global variable can be defined outside. It will be defined outside a function in the main code, right? And you could use it outside after defining, or even inside the function without defining it any further. So as long as before calling the function, you have defined this global variable. So for example, if in this case, I call F5, right? So it's going to return, and I'll just print that value here, right? So if I do that, it gave me 10 because I had defined this variable B outside, and hence inside the function. When I called the function, the program already knew that the value of B is 3, right? But if I would have done the same with the local variable A, and I would have tried to access that value outside the function, then it would have shown me an error. So that gives us a very important definition of global variables and local variables. Global variables can be accessed anywhere in the program, but local variables can be accessed only within the function, right? That's the whole point of a local and a global variable. Okay, so I'll now comment this out, and I'll come back to my van der Waals equation. So in the van der Waals equation, I have pressure, volume, A, B, temperature, gas constant. Now, all of these values are some things that I would be using outside the function as well. It's not just necessary that these values are needed just within the function. So it would be a better idea to define these as global variables. So instead of defining pressure, volume, temperature, pressure, A, B, temperature are inside this function, I'll define them outside as global variables, right? So let's take these values over here. So we have pressure as 100 bars, which is 100 into 10 to the power 5, which is 10 to the power 7. So all of these values we'll take in SI units. The van der Waals constants A and B are 0.364 and 4.267 into 10 to the power minus 5. So it's 0.364 and 4.267 into 10 to the power minus 5, right? And R is the universal gas constant, which is 8.314 joule per mole Kelvin, all in SI unit. And temperature is 500 Kelvin, once again in the SI unit, right? So that is what we have defined over here. And then now we are trying to solve this using fsolve. We are trying to get the value of volume, right? So we'll store that volume in the variable, let's say V, right? And that is going to be sp.fsolve, right? And then I'll put the function name. The function name here is VDW, right? And there has to be an initial guess. Now, the initial guess in this case, there is a physical initial guess that you can take. And if you remember, we did that in the Newton-Raphson video as well, which was the ideal gas volume, right? We took that as the initial guess. So we would do the same thing. So ideal gas volume, RT by T, is what we are going to take as the initial guess. And we'll pass it as an initial guess in this problem, right? And this, as I told you, this returns an array. So since there is just a single value that is going to return, so this is going to be the value of the volume that has been calculated by van der Waals equation of state, right? So now if you see, the ideal gas volume is 0.000415 meter cubes, which is meter cubes per mole, which is approximately 0.4 liter per mole, right? And the van der Waals volume that you've calculated is 0.00037 or 0.37 liters per mole, right? So that's a very useful thing, and that's a good application of the fsolve function, right? Um, you could also do this that you could evaluate these volumes at various pressures and see how the ideal gas and the van der Waals equation deviate, the volume calculated using ideal gas equation and the van der Waals equation are different at different values of pressure. So you could do that by making an array for pressure, right? So we could make a pressure array, which is, let's say, 1 Pascal, 10 Pascal, 100 Pascal, 1000 Pascal, 10,000 Pascal, uh, 10 to the power 5, 10 to the power 6, and 10 to the power 7, right? We've done that. And after that, we are going to put all of this in, put all of this inside an array, inside a loop, right? So for P in PA, right? So we'll do this, and naturally we need to store these values somewhere. So let's make VA an empty list and VIGA, right? And we'll just append these values to these arrays, right? So v dot append, and naturally this has to be the value that you just appended, so -1, right? Yeah, so that is what you can do, and after that we can plot these things. So let's just import matplotlib dot pyplot as plt, and then let's make a legend plot. So plt dot plot, or okay, plt dot plot pressure of the pressure has to be in the y-axis PV diagram. So we'll have VA, which is the volume evaluated from van der Waals, and PA, which is the pressure, and the label is going to be van der Waals, right? And plt dot plot VIGA, comma PA, and the label is going to be ideal gas, right? And plt.legend, plt.x label, we can do all of these things, right? X label, X has a volume in meter cubes per mole, right? And plt.y label, y-axis has pressure in pascals, right? And plt dot show. So these at higher pressures we have this. I am not able to see the volumes at lower, the differences between ideal and van der Waals. Maybe let's just do this for a fewer data points, and maybe we'll see these differences. Yes, so over here we see the difference between the two of them, right? And maybe if we go on to plot another data point, maybe. Okay, now we don't really see the difference, right? So yeah, I think orders of magnitude wise, you will not really see much difference over there, but you can definitely see that the ideal gas pressures and volumes, the ideal gas and the van der Waals volumes are different. The van der Waals is a lot lesser, right? So you can do this for multiple values, right? And yeah, you could evaluate these values for all of them, right? So this is something that I wanted to share. You could also use fsolve to evaluate volumes, temperatures, pressures for other more complicated equations of state, which I mean, for which you may not be able to find analytically expressions analytically, right? Uh, as I also mentioned, that this problem has already been discussed before in the thermodynamics lecture series. So in that we had used Newton-Raphson method, and I highly encourage you all to try and solve this problem using Newton-Raphson method, and this time use Python to code for the Newton-Raphson method. That will be a very good exercise and a good practice in this area. So hopefully you've learned something. We'll keep on doing more such exercises, more such problems using Python. Please do keep practicing, and in case you have doubts, you can reach out to me through your through the email that I've mentioned in the description, or you could just put a comment in the comment section. Thank you so much.